Space is a story told by a universe that loves plot twists. We look up with our best theories, our most advanced technology, and a deep confidence in our understanding, only for the cosmos to reveal a truth so bizarre it leaves the world's top experts speechless. This is a journey through 35 of those breathtaking moments, a countdown of the time space itself broke the rules we thought it followed. By the end, you will have a front-row seat to the greatest surprises in cosmic history, moments that did not just add to our knowledge but shattered entire textbooks. We will see how a world imagined as a tropical paradise turned out to be a crushing oven, and how a signal from the void arrived with such perfect, artificial precision that it has never been explained. Each story is a humbling reminder that the universe is far stranger, more creative, and more mysterious than we ever dared to assume. Are you ready to have everything you thought you knew about space turned upside down? Our first stop on this tour of cosmic surprises begins with a world that was supposed to be familiar. For centuries, Venus was not a mystery but a promise. Astronomers saw its thick, brilliant clouds and its similar size to Earth, and they drew a logical, beautiful conclusion. Here was our sister planet, they reasoned, a place where those clouds meant rain and a gentle climate. The popular imagination filled it with steamy jungles, swampy continents, and perhaps even alien civilizations thriving in a permanent tropical age. It was the ultimate cosmic mirror, reflecting not our reality but our hopes for another Eden just next door. Then we pointed our first real tools toward it, and the mirror shattered. The initial clues came from radio telescopes in the late 1950s, detecting strange emissions that suggested a surface far hotter than anyone had predicted. But the definitive shock arrived with the Mariner 2 spacecraft in 1962. As it flew by, its instruments sent back a data point that rewrote a planet's story in a single number. The surface temperature was not a balmy 80 degrees, it was closer to 800. This was not a tropical world, it was an oven set to broil. The following decades of Soviet Venera probes only deepened the nightmare. These rugged landers, designed to survive the impossible, transmitted back images of a barren, rock-strewn landscape under an oppressive orange sky before succumbing within minutes. They confirmed an atmosphere so thick it exerts a pressure 90 times greater than Earth's, equivalent to being nearly 3,000 feet underwater. The beautiful clouds were not made of water vapor but of corrosive sulfuric acid. This was the stunning reveal. Venus had undergone a runaway greenhouse effect, a process where trapped solar heat created a feedback loop that boiled away any ancient oceans and turned the entire world into a pressurized, scorching hellscape. The experts presumed paradise was in fact a chilling warning of how delicate a planet's balance truly is. The cosmic twin we thought we knew had become our number one surprise, a lesson in humility written in fire and acid. But if Venus taught us the danger of assumptions, Mars delivered a lesson in patience. For generations, the red planet was viewed as the opposite of that lost paradise, a dry, dusty, and utterly dead world. This view was only briefly interrupted by a famous misunderstanding. In the late 19th century, astronomer Percival Lowell pointed his telescope toward Mars and believed he saw something astonishing, a network of straight lines crisscrossing the planet. He called them canals, and he passionately argued they were the work of a desperate, intelligent civilization channeling water from polar ice caps to save their dying world. It was a captivating story, but it was wrong. Better telescopes revealed the canals to be an optical illusion, a trick of the eye connecting distant, blurry surface features. Mars was cast back into silence, a lifeless desert locked in permanent freeze. The experts settled on a quiet, barren planet, its story seemingly over. Then our robotic eyes arrived in orbit. The Mariner 9 spacecraft in 1971 became the first to map the entire planet, and its cameras saw what telescopes never could. The images were not of neat, artificial canals, but of something far more natural and profoundly more shocking. They revealed vast, winding channels that could only be ancient river valleys. They showed sprawling, fan-shaped deltas where water had once emptied into long-vanished lakes. They captured the scars of catastrophic floods where ancient banks had been torn open to release torrents across the plains. The Viking orbiters that followed painted an even clearer picture. Here was the undeniable evidence not of a present civilization but of a lost world. Mars had not always been this dry husk. Billions of years ago, it had rivers that flowed, lakes that pooled, and a thick atmosphere that could support liquid water on its surface. This was not a minor discovery, it was a complete rewrite of planetary history. The search for life was transformed in an instant. We were no longer looking at a dead rock, but at a world that had once held the key ingredient for life as we know it for hundreds of millions of years. The question shifted from if life could exist on Mars to where it might have left its traces. Every rover mission since, from Pathfinder to Curiosity to Perseverance, has been a direct result of that stunning orbital surprise, following the ghostly watermarks toward an answer. The story of water on Mars rewrote a world's past, but the next surprise was rewriting the rules of geology itself. For a long time, our solar system's moons were seen as quiet, frozen relics. They were captured asteroids or ancient rubble, cold and geologically dead, their surfaces etched only by the occasional impact crater. They were places where nothing changed for billions of years. Then, in March of 1979, the Voyager 1 spacecraft turned its cameras toward a small, orange-tinted world orbiting Jupiter, a moon named Io. The imaging team was expecting another cratered ball of ice and rock, just another day to point in a long survey. What appeared on their monitors was nothing short of impossible. There, against the blackness of space, were distinct umbrella-shaped plumes. They were not impact features or atmospheric tricks. They were volcanic eruptions, actively spewing material hundreds of kilometers above the surface. In an instant, the assumption of dead moons was shattered. Io was alive, violently and spectacularly alive, boasting the first active volcanoes ever seen beyond Earth. The shock rippled through the scientific community. How could a moon so small, so far from the sun's warmth, generate such ferocious heat? The answer was a masterclass in cosmic mechanics. Io's volcanoes are not powered by a molten core in the way Earth's are, but by a relentless gravitational tug of war. As Io orbits Jupiter, the immense gravity of the giant planet pulls on it, but so do the gravitational influences of neighboring moons Europa and Ganymede. This creates an orbital dance that is not perfectly circular. Io is constantly being stretched and squeezed, its very interior flexing like a ball of clay in an invisible hand. This friction generates tremendous internal heat, a process called tidal heating. That heat has to escape, and it does so through hundreds of active volcanoes and lava lakes that constantly resurface the moon, making Io the most volcanically active body in our entire solar system. It is a world of fire born from orbital rhythm, a stunning demonstration that even in the cold outer reaches, celestial forces can forge a landscape of astonishing, eruptive beauty. Io's violent rebirth taught us that moons could defy expectations, but Saturn would present a mystery of pure, chilling geometry. While Voyager's glimpse of Io was a revelation of heat and motion, its cameras also caught something else on the gas giant Saturn, a fleeting, blurry anomaly at the North Pole that seemed too strange to be real. The images suggested a vast, six-sided cloud pattern, a perfect hexagon etched into the planet's atmosphere. It was so geometrically precise, so utterly unnatural looking against the chaotic swirl of gas giants, that many dismissed it as a trick of light or a camera artifact. The idea that a planet's atmosphere could organize itself into a giant, persistent polygon seemed to violate every law of fluid dynamics. Storms are supposed to be circular, swirling vortices, not rigid geometric shapes. Yet, when the Cassini spacecraft arrived over 2 decades later, it did not find a temporary illusion. It found the hexagon still there, waiting. Cassini's detailed view was breathtaking. This was a structure wider than 2 Earths, a 6-sided jet stream with winds screaming at over 300 miles per hour, each wall a sheer cliff of cloud. And it was stable. It had been there, churning in the same perfect shape for at least 30 years and likely far longer. This was not just a storm, it was a permanent atmospheric feature, a piece of planetary jewelry with mathematical precision. The explanation, while still not complete, points to a fascinating experiment in planetary scale. Researchers believe the hexagon is a standing wave pattern, a kind of stable ripple in Saturn's fast-moving north polar jet stream. Think of it like the harmonic that forms when you vibrate a plate of water, creating a standing pattern of peaks and valleys. On Saturn, the deep atmosphere and the planet's own rotation may create the conditions for this single, 6-sided wave to lock into place, a geometric tattoo stamped onto a world of gas. Yet, the full depth of its stability and perfection remains one of the solar system's most visually stunning puzzles. It is a reminder that the universe has a flair for artistry, crafting not just random beauty, but patterns of such ordered elegance that they seem to belong more to a mathematician's dream than to the turbulent skies of a distant world. The geometric perfection of Saturn's hexagon feels almost like a cosmic signature, a deliberate pattern stamped onto chaos. But what if the greatest signature of all is not found on a planet or in a storm, but in the very fabric of nothingness itself? For centuries, the void of space was considered exactly that, an empty stage where matter and light performed. Yet modern physics delivered a shock that redefined emptiness. According to quantum theory, what we call a vacuum is not empty at all. It is a seething, bubbling sea of potential. At the tiniest imaginable scales, particles and their anti-particle counterparts are constantly flickering into existence and annihilating each other in an instant. These are quantum fluctuations, and they imbue every cubic centimeter of so-called empty space with a background energy, known as vacuum energy. This is not just a theoretical curiosity, it has a real, measurable effect. It should be pushing on the very structure of the universe. The surprise, the monumental shock for cosmologists, came when they tried to calculate how strong this push should be. When you add up all the potential energy from these quantum fluctuations across the vastness of space, the number you get is absurd. It suggests a vacuum energy so unimaginably powerful that it should have ripped the universe apart in its first fraction of a second, preventing stars, galaxies, or anything else from ever forming. The universe we see, stable and structured over billions of years, should be impossible. Yet here we are. This is where observation delivered its stunning verdict. In the late 1990s, astronomers discovered the expansion of the universe is not slowing down, as everyone expected, but accelerating. Something is pushing galaxies apart faster and faster. That something is called dark energy. When they measured the strength of this dark energy, the actual force driving cosmic acceleration, the number was tiny, almost negligible compared to the universe-tearing prediction from quantum vacuum energy. But it is not zero. The discrepancy between these two numbers is the largest mismatch in the history of science. The vacuum energy predicted by quantum physics is about 120 orders of magnitude. That is a 1 followed by 120 zeros, stronger than the dark energy we observe. This is not a small error. It is a catastrophic disagreement that tells experts they are missing something profound, a fundamental piece of reality that connects the quantum world to the cosmos. The void, it turns out, holds the greatest unsolved puzzle in physics, a silent, pervasive energy whose true nature remains the universe's most guarded secret. While dark energy whispers of mysteries in the void, our own cosmic backyard holds a different kind of secret, one written in ice. For centuries, the sudden, brilliant appearance of a long-period comet was a source of awe and sometimes fear. These visitors would blaze across the sky with immense, sweeping tails, only to vanish back into the darkness for thousands, even millions of years. They followed orbits so vast and elliptical they seemed to come from nowhere, a deep and empty space far beyond the planets. Where was their home? Astronomers knew these icy wanderers must be stored somewhere, a cosmic reservoir holding them in frozen suspension until a subtle gravitational nudge sent one falling sunward. But the location of that reservoir was a profound puzzle. The answer came from Dutch astronomer Jan Oort in 1950. Studying the paths of these comets, he proposed a stunning idea. He suggested the solar system does not end with Pluto, or even with the scattered disk of objects we now call the Kuiper Belt. Instead, he theorized a vast spherical shell of icy remnants enveloping our entire planetary system, a cloud so distant and diffuse it had never been seen. This was the Oort cloud, and its proposed scale was the first great surprise. Oort calculated that this shell begins roughly 2,000 times farther from the Sun than Earth and extends outward for an almost incomprehensible distance, nearly halfway to the next star. Our Sun's gravitational influence, it turns out, stretches across a full light year of space. This means the true boundary of our solar system is not a neat line near the last planet, but a fading sphere of gravitational dominance containing trillions, perhaps even quadrillions, of icy objects in a deep freeze that has lasted since the dawn of our system. The second, deeper surprise is what these objects represent. They are not random interlopers. The Oort cloud is a frozen archive, a pristine time capsule from the solar system's violent birth. When the giant planets like Jupiter and Saturn formed, their immense gravity acted like a cosmic slingshot, flinging countless icy planetesimals, the building blocks of worlds, out into these distant, looping orbits. There, in the profound cold and stillness, they have remained, virtually unchanged for 4.5 billion years. Every long-period comet that graces our sky is a piece of that original construction material, gently deflected from its resting place and sent on a long fall into the light. So, the next time you see a comet with a tail stretching across the heavens, remember you are not just looking at a beautiful spectacle. You are witnessing a page from the solar system's first chapter, delivered from a hidden, icy vault at the very edge of the Sun's realm. The Oort cloud is a frozen library of our past, but to understand the present engine of our solar system, we must look to the Sun. For decades, physicists thought they had its core process perfectly mapped. The Sun shines through nuclear fusion, where hydrogen atoms fuse into helium, releasing energy and, as a byproduct, a flood of nearly massless particles called neutrinos. These ghostly particles should stream out from the solar core, passing through the Sun and Earth almost as if they were not there. By the 1960s, scientists had built ingenious detectors deep underground to catch just a few of these solar neutrinos, using massive tanks of cleaning fluid or water. The goal was simple: confirm the theory of how the Sun makes its light. The results, however, were anything but simple. The detectors consistently found only about 1/3 of the neutrinos their models predicted. This was the solar neutrino problem, and it created a profound crisis in physics. For over 30 years, experts faced a troubling dilemma. Either our fundamental understanding of how the Sun works was completely wrong, or our understanding of the most basic particles in the universe was flawed. It cast a long shadow of doubt. Was the Sun's core cooler than we thought? Were our models of stellar fusion incorrect? The discrepancy was too large to ignore, suggesting a fundamental crack in our knowledge of either the cosmos or the quantum world. The resolution, when it finally came, was a stunning surprise that no one had fully anticipated. The answer was not with the Sun, but with the neutrinos themselves. Theorists had proposed a wild idea that neutrinos might not be static. They could oscillate or change between 3 different types or flavors as they traveled through space. But for this to happen, a revolutionary condition had to be true. Neutrinos had to have a tiny amount of mass. This was a direct violation of the long-established standard model of particle physics, which stated neutrinos were massless. The definitive proof came from two major experiments at the turn of the century: the Super Kamiokande detector in Japan and the Sudbury Neutrino Observatory in Canada. Their incredibly precise measurements showed conclusively that the missing solar neutrinos had not vanished. They had simply changed into types that earlier detectors could not see. The Sun was producing exactly the number of neutrinos predicted. They were just shape-shifting on their journey to Earth. This discovery was monumental. It solved the 30-year-old mystery not by fixing the Sun, but by rewriting the rules of the universe's smallest building blocks. It proved neutrinos have mass, however minuscule, forcing a major revision of the standard model and opening a new window into the weird, transformative nature of reality itself. The ghostly particles from the Sun had carried a secret about their own identity, a secret that changed physics forever. The Sun's ghostly neutrinos revealed a universe of shifting identities, but to find the oldest light of all, we must look back to the very beginning. If the Big Bang was the first moment, then its afterglow should be the first photograph, a snapshot of the infant universe frozen in time. This glow is the cosmic microwave background, a faint whisper of radiation that fills every corner of space, left over from when the universe cooled enough for light to finally travel freely. For decades, theorists knew what this primordial picture should look like. The early universe, they reasoned, could not have been perfectly smooth. Tiny, random quantum ripples in the dense, hot soup of matter and energy would have created minute variations in temperature, regions that were ever so slightly hotter or colder than their surroundings. These tiny seeds, stretched by the universe's expansion, would become the gravitational wells where galaxies and clusters would eventually form. The map of the modern cosmos, with its vast voids and glittering superclusters, should be written in the faint temperature differences of this ancient light. So, when NASA Cosmic Background Explorer satellite, COBE, was launched in 1989, the entire astrophysics community held its breath, waiting to see these predicted wrinkles in the fabric of spacetime. The initial result was not a confirmation, but a shock of cosmic proportions. The COBE data revealed a background that was astonishingly, almost unnervingly smooth. The temperature was the same in every direction to an incredible degree of precision. It was a uniform sea of microwave light, a picture of near-perfect harmony. This was a profound problem. A universe that smooth could not have given rise to the lumpy, structured cosmos we see today. It was too perfect to be true, suggesting our models of cosmic evolution were missing a critical ingredient. The experts were faced with a background so uniform it threatened to erase the story of our own existence. The resolution to this puzzle came from looking closer, much closer. COBE instruments were groundbreaking, but they were like viewing a masterpiece painting from across a football field. You could see it was there, but not the delicate brushstrokes. The follow-up missions, the Wilkinson Microwave Anisotropy Probe and later the Planck satellite, were designed to bring the universe's first portrait into exquisite focus. When their data finally streamed back, they delivered a surprise that was the perfect counterpart to the first. Etched into that smooth background at a level of detail 1 part in 100,000 were the predicted fluctuations. The universe's baby picture was not a blank canvas, it was a pointillist masterpiece of tiny hot and cold spots, a precise map of density variations that perfectly matched the seeds needed to grow every galaxy, star, and planet we see. This was the universe's blueprint, confirmed with stunning accuracy. The journey from COBE's shocking smoothness to Planck's detailed map taught us a humbling lesson that the cosmos often presents us with a paradox first, a picture so simple it seems to break everything, only to reveal its profound complexity upon a closer, more patient look. The universe's first portrait was a map of gentle beginnings, but the modern galaxy holds evidence of a far more violent kind of birth. For centuries, astronomers understood the graceful, stately dance of stars within the Milky Way, all bound by gravity in a vast, swirling disk. Their speeds were predictable, governed by the immense pull of the galaxy's core and its halo of dark matter. A star could move quickly, certainly, but never fast enough to break free from the Milky Way's gravitational embrace. That was an unbreakable rule until it was not. The discovery came not from watching a star's motion across the sky, but from carefully measuring its light. By analyzing the subtle shift in a star's spectrum, its Doppler shift, astronomers can calculate its speed directly toward or away from us. In the early 2000s, researchers pointed their instruments at stars in the galactic halo, the sparse outer region of our galaxy, and found something that defied all expectations. They identified stars moving at staggering velocities, over 1 million miles per hour. These were not just fast stars, they were projectiles. Their speed was so great it exceeded the Milky Way's escape velocity, meaning they were not in orbit at all. They were on a one-way trip out, blazing a trail into the intergalactic void, destined to wander the darkness between galaxies forever. The immediate question was how? What cosmic catapult could possibly impart such an incredible velocity to an object as massive as a star? The leading theory points to the most violent engine at the heart of our galaxy, the supermassive black hole known as Sagittarius A star. Here is how the incredible ejection is thought to work. Imagine a binary star system, two stars orbiting each other, drifting too close to the black hole's immense gravitational field. The black hole's tidal forces can tear the binary pair apart, capturing one star into a tight orbit while violently flinging the other away at a tremendous speed. It is a gravitational slingshot of unimaginable power. These hypervelocity stars are the celestial shrapnel from a catastrophic encounter, their very existence serving as direct evidence of the chaotic dynamics happening right in our galactic center. They are living proof that the quiet disk of the Milky Way is occasionally punctuated by these explosive events, where stars are not born but launched, becoming eternal travelers cast out from their home. If hypervelocity stars are the shrapnel flung from a galactic explosion, then the next discovery proved that entire worlds could emerge from the ashes. The search for planets beyond our solar system had for decades focused on stars like our own sun, stable and long-lived, the kind of nurturing hearths where life seemed most likely to take root. It was a logical, almost hopeful place to look. Then, in 1992, astronomers Alexander Wolskson and Dale Frail made an announcement that shattered that comforting assumption. They had found the first confirmed planets outside our solar system, but they were not orbiting a gentle yellow sun. They were circling a pulsar, a cosmic zombie. A pulsar is the super-dense, rapidly spinning corpse of a massive star that has died in a supernova explosion, an event of almost unimaginable violence that should have sterilized its entire vicinity. This particular pulsar, named PSRB 1257+12, spins hundreds of times per second, blasting out deadly beams of radiation like a relentless celestial lighthouse. The very idea of planets in such an environment seemed absurd, a cosmic joke. How could anything, let alone a delicate orbiting system, survive the stellar apocalypse that created the pulsar in the first place? The discovery forced experts to completely rethink the concepts of planetary resilience and formation. Two startling possibilities emerged. The first is a story of survival against all odds. Perhaps these are the charred remnants of the original planetary system, the inner cores of giant planets that somehow held on through the supernova's fury, their outer layers blasted away, leaving behind scorched, rocky skeletons still tracing their ancient orbits. The second possibility is even more astonishing, a story of rebirth from ruin. The supernova would have left behind a vast, swirling disk of heavy elements and debris, the remains of the shattered star. From this apocalyptic cloud of dust and gas, a second generation of planets could have coalesced, newborn worlds forged not in the calm of a stellar nursery, but in the radioactive aftermath of a star's death. These pulsar planets, bathed in constant, lethal radiation, are utterly inhospitable to life as we know it, yet their existence is a profound revelation. It tells us that planet formation is not a gentle, singular event, but a stubborn, ubiquitous process that can happen in the most extreme environments imaginable. The universe, it seems, will make planets anywhere, even in the graveyard of a star. The pulsar's planets were a testament to cosmic resilience, but the next signal seemed to be a deliberate call. On a quiet August evening in 1977, at Ohio State University's Big Ear radio telescope, a routine sky survey was underway. The system printed its data on long, continuous sheets of paper, a simple string of letters and numbers representing signal strength. For the most part, the printout was a monotonous sequence of background noise, the gentle hiss of the universe. Then, just after 10:16 p.m., the system recorded something extraordinary. For exactly 72 seconds, the telescope's fixed gaze swept across a point in the constellation Sagittarius, and the data spike was so intense, so perfectly formed, that volunteer researcher Jerry Amon, reviewing the printout days later, circled the alphanumeric sequence in red pen and wrote a single, emphatic word in the margin: "Wow." The signal itself was a marvel of precision. It was a strong, narrowband radio emission at exactly 1,420 MHz, a frequency that is notably quiet, protected by international agreement from earthly broadcasts because it happens to be a natural emission line of hydrogen, the most common element in the universe. Any advanced civilization, the thinking went, might logically use such a universal, quiet channel to announce its presence. The wow signal fit that hypothetical profile perfectly, a brief, powerful shout on a cosmic calling card. The surprise and ensuing mystery were profound. The Big Ear had 2 feed horns, and the signal appeared in only one as the sky drifted through its beam, exactly as expected for a genuine extraterrestrial source. It had all the hallmarks of an artificial beacon, and then it vanished, despite decades of dedicated searches by countless telescopes pointed at that same spot in the sky. The signal was never heard again. No natural astronomical phenomenon, from a passing comet to a stellar flare, has ever satisfactorily explained its unique characteristics. It remains a solitary, tantalizing anomaly, a one-of-a-kind event that lasted less than 2 minutes but has echoed for decades in the human imagination. It stands as the purest mystery in the history of the search for extraterrestrial intelligence, a perfect candidate that arrived, announced itself with stunning clarity, and then retreated back into silence, leaving behind only a circled code on a faded printout and a profound, unanswered question hanging in the static of the stars. The wow signal was a perfect mystery, a whisper of possibility that faded before we could understand it. Yet another discovery, made just a few years later, would not fade. It would rewrite the ultimate destiny of everything. For most of the 20th century, the cosmic story had a clear and tragic ending. The universe began in a big bang and had been expanding ever since. The central question for cosmologists was not if it was expanding, but how that expansion would end. Gravity, the great attractive force binding galaxies and clusters, was constantly pulling back on that initial outward rush. The universal expectation was that this gravitational break would be slowing the expansion down. The only debate was by how much. Would the slowdown be enough for gravity to eventually win, pulling all matter back together in a catastrophic big crunch? Or would the expansion simply coast toward a slow, cold halt? The answer would determine the final fate of all existence, and in the late 1990s, 2 independent teams set out to measure this cosmic deceleration with unprecedented precision. Their tool was a specific kind of stellar explosion, a Type 1 supernova. These are known as standard candles because they always explode with roughly the same intrinsic brightness. By observing how dim such a supernova appears from Earth, astronomers can calculate its exact distance. By then measuring the redshift of its light, which tells us how much the universe has stretched since the explosion, they can determine how fast the universe was expanding at different points in its history. The goal was to compare supernova from billions of years ago to more recent ones, plotting the slowdown of cosmic expansion over time. The teams, led by Saul Perlmutter and separately by Brian Schmidt and Adam Rees, painstakingly collected their data from the most distant explosions they could find. When they finally compared their results, they faced not a confirmation but a shock that overturned cosmology. The distant, ancient supernova were fainter than they should have been. This meant they were farther away than the slowing expansion model predicted. The only possible explanation was that the universe's expansion was not slowing down at all. It was speeding up. Something was pushing galaxies apart faster and faster, overwhelming the pull of gravity itself. This was like throwing a ball into the air and watching it not only fail to fall back down, but shoot away from you at an ever-increasing velocity. The discovery was so startling, so contrary to all expectation, that both teams spent years checking and rechecking for errors, from dust in space to flaws in their instruments. But the data was undeniable. In 1998, they announced their Nobel Prize-winning conclusion: the expansion of the universe is accelerating. The force behind this acceleration was given a name that confessed our ignorance: dark energy. This invisible, repulsive pressure now appears to make up about 68% of all the energy in the cosmos, dictating its long-term fate. Instead of a fiery crunch or a frozen halt, the universe now seems destined for a cold, lonely, and ever-accelerating drift into infinite separation, a silent fade dictated by a force we have only just begun to name. The universe's accelerating expansion paints a future of infinite drift, but our own moon held a secret that could anchor a human future. For centuries, the moon was the definitive symbol of a dead, dry world. Its surface, pockmarked and gray, showed no sign of atmosphere, no hint of erosion, and certainly no evidence of the one ingredient essential for life as we know it. Every rock sample brought back by the Apollo astronauts was bone dry. The scientific consensus was absolute: the moon was a cosmic desert, completely and utterly devoid of water. This belief shaped our plans for it, limiting visions of lunar bases to bleak, entirely self-sufficient outposts where every drop of water would have to be hauled from Earth at staggering cost. Then, in the 1990s, two robotic scouts began to whisper a different story. The Clementine mission in 1994 bounced radio waves off the lunar surface, and its data hinted at something highly reflective in the deep, permanently shadowed craters at the moon's poles, regions where the sun never rises and temperatures hover near absolute zero. The Lunar Prospector mission that followed a few years later carried a neutron spectrometer, an instrument that could sense the presence of hydrogen. As it mapped the poles, it found strong signals suggesting vast deposits of hydrogen locked in the soil, the most logical source for that hydrogen: water ice. The evidence was indirect but compelling, a ghostly signature in the data that challenged the dry moon dogma. To settle the debate, NASA designed a dramatic experiment. In 2009, they sent the Lunar Crater Observation and Sensing Satellite, LCROSS, on a kamikaze mission. It targeted a permanently shadowed crater at the South Pole called Cabeus and sent a spent rocket stage crashing into its depths at over 5,000 miles per hour. The LCROSS spacecraft, following just behind, flew through the resulting plume of ejected material, analyzing its contents with exquisite precision before it too impacted the surface. The data it sent back in its final moments was definitive. The plume contained not just hints of water, but a significant amount, with measurements suggesting the crater floor could be several % water ice by weight. The surprise was total. The moon was not dry after all. It harbored vast frozen reservoirs in its coldest, darkest corners, ice preserved for billions of years, likely delivered by ancient comet impacts. This discovery transformed everything. Water is not just for drinking, it is oxygen for breathing and hydrogen for rocket fuel. Finding it on the moon meant a permanent human presence was no longer a fantasy of endless supply chains from Earth, but a realistic possibility of living off the land. Those shadowed craters, once seen as the most desolate places on the moon, suddenly became the most valuable real estate in the solar system, the oases that could fuel humanity's next giant leap. The discovery of water ice on the moon offered a promise of future sustenance, but on Mars, a different trace gas has sparked a debate about the possibility of past or even present life. For years, our understanding of the Martian atmosphere was one of a thin, chemically simple blanket, dominated by carbon dioxide and seemingly inert. Then, in 2003, the European Space Agency's Mars Express orbiter made an announcement that sent a ripple of excitement through the scientific community. Its instruments had detected small, localized pockets of methane gas in the Martian air. This was not just another atmospheric component, it was a profound surprise. On Mars, methane is a fragile molecule. The thin atmosphere allows intense ultraviolet sunlight to break it apart, meaning any methane released should be destroyed within a few hundred years. Finding it at all means something on Mars is actively producing it right now, or at least very recently. It is a gas that should not be there, and its presence points to an active modern process hidden beneath the rusty surface. The intrigue only deepened because of what methane means here on Earth. While it can be produced by non-biological processes like certain rock-water reactions known as serpentinization, a significant portion of Earth's atmospheric methane is belched out by living organisms, from microbes in wetlands to the digestive systems of cattle. Its detection on another world immediately raises the tantalizing question, could this be a signature of Martian biology? The plot thickened with the arrival of NASA Curiosity rover in Gale Crater. Unlike an orbiter taking a snapshot of the whole planet, Curiosity could take a long-term, ground-level census of the air. Its measurements revealed something even more puzzling. The methane did not behave as expected. Instead of a steady, low background, the rover detected sudden, sharp spikes where methane levels would increase by a factor of 10 and then vanish just as quickly. These transient plumes were like brief, mysterious exhalations from the planet itself, localized puffs of gas that appeared and dissipated before their source could be pinpointed. This behavior defies easy explanation. If the source were a widespread, steady geological process, we would expect a more constant, diffuse presence. These sharp spikes suggest localized, perhaps even episodic, vents. The debate over the source is a modern astrobiological detective story with two compelling suspects. The geological explanation involves water interacting with certain minerals like olivine deep underground, a process that can produce methane without any life involved. The biological explanation, of course, points to subsurface microbial communities, perhaps hidden in briny aquifers, producing the gas as a byproduct of their metabolism. Recent data has added more twists, with the European Trace Gas Orbiter, designed specifically to study methane, reporting it has found none at all in the global atmosphere, deepening the mystery of why Curiosity sees those sporadic spikes. This discrepancy itself is a clue, suggesting the gas is being destroyed or dispersed even faster than we thought, or that the sources are so localized and brief they escape orbital detection. The methane on Mars is more than just a gas, it is a ghost. It appears, hints at incredible possibilities, and then fades before we can grasp its origin. It is a puzzle written in the thin Martian air, a whisper that the red planet, so seemingly quiet, might still hold active secrets in its depths. While methane whispers of hidden activity on Mars, Jupiter broadcasts its power with a storm that has raged for centuries. The Great Red Spot is an icon of our solar system, a swirling crimson vortex so vast that our entire planet could fit comfortably inside it. This is not a transient weather event. It is a permanent fixture of Jupiter's atmosphere, observed by astronomers since at least the 1600s when telescopes first turned toward the giant planet. Its sheer longevity is the central surprise, a mystery written in gas. On Earth, even the most powerful hurricanes are fueled by warm ocean water and dissipate within days or weeks once they move over land or cooler seas. Jupiter has no solid surface to break up a storm's circulation, but even in a fluid atmosphere, physicists expected such colossal systems to lose energy, to gradually slow down and fade away due to turbulence and friction. Computer models consistently predicted the Great Red Spot should have vanished centuries ago. Yet there it spins, a defiant, ancient maelstrom that has outlasted empires. The key to its endurance lies in its unique dynamics. Unlike a terrestrial hurricane, which is a bottom-up system drawing energy from below, the Great Red Spot is a high-pressure anticyclone, a massive, cold, elevated pancake of gas. It is wedged between two of Jupiter's powerful east-west jet streams, which constantly feed energy into it like river currents stabilizing a giant whirlpool. It is also remarkably shallow for its width, perhaps only a few hundred kilometers deep compared to its 16,000-kilometer breadth. This structure allows it to persist, a self-sustaining atmospheric engine locked in a perpetual dance with the winds around it. But even this titan is not unchanging. Modern observations from spacecraft like Voyager, Galileo, and Juno have shown the spot is slowly shrinking and becoming more circular, and its iconic red color, likely caused by chemicals being uplifted from deeper layers and broken apart by sunlight, has varied in intensity over time. Studying it is like watching a slow-motion lesson in fluid dynamics on a planetary scale. Each new measurement helps scientists understand not just Jupiter, but the fundamental behavior of storms in gas giants across the galaxy, making this centuries-old tempest one of our most enduring teachers in the sky. The Great Red Spot is a lesson in endurance, a storm that has witnessed centuries of human history from its perch on Jupiter. But in the vast nurseries where stars are born, time moves to a different, more destructive rhythm. One of the most famous and beautiful images ever taken by the Hubble Space Telescope is known as the Pillars of Creation. Captured in 1995, it shows three towering columns of cold, interstellar gas and dust, light years in length, rising like cosmic mountains within the Eagle Nebula. Bathed in the ultraviolet light from nearby massive young stars, their silhouettes are etched against a glowing backdrop, with delicate streamers of gas evaporating from their surfaces. The name was perfect, for nestled within those dark, dusty pillars, new stars were actively forming, their birth hidden from our optical view. The image became an icon, a symbol of the universe's creative, nurturing power, a place where the raw materials of existence coalesced into new suns. It felt eternal, a celestial cathedral frozen in a moment of glorious genesis. That sense of permanence was the first great illusion. The pillars are not a static monument, they are a temporary structure in an ongoing battle. The same brilliant stars whose light makes the pillars glow so beautifully are also destroying them. Their intense radiation acts like a cosmic blowtorch, boiling away the gas in a process called photoevaporation, carving the intricate shapes we see and stripping material from the pillars' surfaces. This erosion was understood, part of the dramatic story the image told, but a deeper, more startling surprise was waiting in a different kind of light. When the Spitzer Space Telescope, designed to see the infrared universe, turned its gaze toward the Eagle Nebula, it revealed a hidden chapter. Its instruments detected a vast cloud of dust, heated to incandescence, billowing around the region. The pattern and temperature of this dust suggested it had been superheated by a powerful shockwave, the expanding front of a supernova explosion. Based on the apparent speed and scale of this shockwave, astronomers made a startling calculation. A massive star in that region likely went supernova between 6 and 9,000 years ago. The resulting blast wave, traveling at millions of miles per hour, would have reached the position of the pillars of creation roughly 1,000 years ago. From our vantage point on Earth, located 7,000 light-years away, the light from that cataclysm has not yet reached us, but the infrared evidence is a ghost from the future. The logical, heartbreaking conclusion is that the iconic pillars, as we know and love them from the Hubble image, have probably already been swept away, shredded by that interstellar tsunami. We are looking at a mirage of the past, a photograph of a structure that may no longer exist. This is the poignant lesson written in the pillar's light. The universe is in constant, violent motion, and we are always watching history unfold. The beauty we capture is often a farewell portrait, a reminder that creation and destruction are two sides of the same cosmic coin, and that sometimes the most stunning vistas are also elegies for wonders already gone. The pillars of creation taught us that cosmic beauty is often a fleeting glimpse into the past, but another discovery closer to home forced us to rewrite the present map of our own solar system. For generations, every child learned there were 9 planets, with tiny, distant Pluto holding a cherished place at the very edge, a lonely sentinel in the dark. Its status as our 9th world seemed as permanent as the Sun itself, a fixed point in our understanding. This certainty began to crumble in the late 1990s as astronomers equipped with powerful new digital cameras began a systematic survey of the sky beyond Neptune. They were searching for faint, slow-moving objects, and they found them. Not just one or two, but dozens, then hundreds. A whole new class of icy worlds was emerging from the darkness, orbiting in a vast, donut-shaped region we now call the Kuiper Belt. This belt is a cosmic junkyard of frozen leftovers from the solar system's formation, and its existence was a profound confirmation of theoretical predictions. But the real shock came in 2005. A team led by astronomer Mike Brown announced the discovery of an object even more distant than Pluto, temporarily named Xena, but soon officially called Eris. Initial measurements suggested it was slightly more massive than Pluto. This was the catalyst for a crisis in planetary identity. If Pluto was a planet, then surely Eris, its equal, must be one too. And if Eris was a planet, then what about the other large Kuiper Belt objects like Makemake and Haumea? Where would the list end? The International Astronomical Union, the body responsible for celestial nomenclature, faced a dilemma. They could either add dozens of new planets to the solar system, or they had to define what a planet actually means. In 2006, after intense debate, they established 3 clear criteria. A planet must orbit the Sun. It must be massive enough for its own gravity to pull it into a round shape, and it must have cleared the neighborhood around its orbit. Pluto and its new cousin Eris easily met the first 2 conditions, but they failed the third spectacularly. Their orbits are crowded with other icy objects in the Kuiper Belt, meaning they have not dominated their gravitational surroundings. This was the surprising, logical conclusion that changed our textbooks overnight. Pluto was reclassified as a dwarf planet, a new category for those round objects that share their orbital space. The emotional surprise for the public was profound, a sense of loss for a familiar cosmic landmark, but the scientific surprise was one of scale and humility. We did not lose a planet, we gained an entirely new understanding of our solar system's architecture. Pluto was not a lonely oddball at the edge, but the king of a vast populous frontier, the largest known member of a whole new family of worlds. Its demotion was not a downgrade, but a promotion to a new role, guiding our exploration into a previously hidden realm of frozen history. Pluto's reclassification revealed a hidden frontier of frozen worlds, but deep within the corpses of massive stars lies a force of pure, unimaginable violence. A neutron star is already one of the most extreme objects in the universe, a city-sized sphere containing more mass than our Sun. crushed so tightly that a single teaspoon of its material would weigh billions of tons. Yet, some of these stellar zombies possess an additional, almost fictional property. They are magnetars, neutron stars with magnetic fields so powerful they defy comprehension. To grasp the scale, Earth's magnetic field is strong enough to guide a compass needle. A typical neutron star's field is 1,000,000,000,000 times stronger. A magnetar's field is another 1,000 times beyond that, a quadrillion times the strength of our planets. If a magnetar were located halfway between Earth and the Moon, its magnetic field would effortlessly strip the data from every credit card on our planet. This is not just a strong magnet, it is a fundamental force of nature given physical form, capable of twisting the very structure of space-time itself. These fields are so intense they place the star's rigid crust under unimaginable strain, and sometimes that crust cracks. On December 27, 2004, satellites orbiting Earth detected a flash of gamma rays so brilliant it temporarily blinded their instruments. The source was a magnetar named SGR 180620, located 50,000 light-years away on the far side of our own galaxy. This was not a simple burst, it was a starquake. The magnetar's crust had undergone a catastrophic shift, a seismic event on a stellar scale, releasing more energy in 1/10 of a second than our Sun emits in 100,000 years. The ripple of that distant cataclysm washed over our solar system. In an instant, the burst of radiation ionized the upper layers of Earth's own atmosphere, disturbing long-range radio communications and physically expanding our ionosphere. Astronomers were left in a state of pure awe. An event on a tiny, distant object no larger than a city had reached across tens of thousands of light-years of empty space and physically touched our planet. It was a humbling demonstration of the raw power locked within these exotic objects, a reminder that the universe conducts physics at volumes we can scarcely hear, and whose occasional shouts can echo clear across the galaxy. The magnetar's starquake was a blast of pure force, but sometimes the universe's greatest tricks are played with light itself. In the constellation Piscis Austrinus, a brilliant young star named Fomalhaut has captivated astronomers for decades, not for the star itself, but for what surrounded it. The Hubble Space Telescope revealed a breathtaking sight, a razor-sharp, icy dust ring circling the star like a cosmic bullseye. This was a protoplanetary disk in exquisite detail, a snapshot of a solar system under construction. But the real prize came in 2008, when Hubble's images revealed a tiny, bright point of light moving along just inside the inner edge of that dust ring. It was a eureka, a moment hailed around the world. After years of inferring planets from wobbles and shadows, here was one of the first exoplanets ever directly photographed, a world caught in the act of orbiting its sun. Named Fomalhaut b, it was celebrated as a landmark discovery, a pristine giant planet sculpting the dust ring with its gravity, a textbook example made visible. For years, it was a jewel in the crown of exoplanet science. Then, astronomers pointed Hubble back for a follow-up look, expecting to trace its continued orbit. What they saw instead was a slow-motion disappearance. The pinpoint of light was not behaving like a planet at all. It was growing fainter. It was also expanding, becoming more diffuse, and its path was drifting away from the star, not following a neat gravitational orbit. The object was not a solid world. It was a cloud, a vast, expanding haze of fine dust. The stunning new interpretation was that Hubble had not captured a planet's birth, but the aftermath of a planetary-scale catastrophe. What we witnessed was likely the colossal collision of two large, icy planetesimals, each perhaps hundreds of miles across. The impact would have been apocalyptic, pulverizing both bodies into a colossal, glowing cloud of vaporized rock and ice that slowly expanded and faded over the years. The surprise was a masterclass in cosmic misinterpretation. From 725 light-years away, the flash of that ancient disaster and the resulting debris cloud appeared for a beautiful, brief window exactly like a single, stable planet. It was a reminder that the universe often shows us only the echo of an event, and our first, most exciting conclusion might just be the opening chapter of a stranger, more violent story. We had not found a new world, but had instead become witnesses to the moment one, or perhaps two, were utterly destroyed. The dust cloud from Fomalhaut's collision was a cosmic illusion, a single snapshot of a fleeting disaster. But another star's story was written not in a single flash, but in a pattern of missing light so bizarre it demanded a search for something permanent, and perhaps intelligent in the dark. In 2015, citizen scientists with the Planet Hunters project, sifting through data from NASA's Kepler Space Telescope, flagged a star that simply made no sense. Labeled KIC 8462852, but soon famously known as Tabby's star after astronomer Tabby Voyager, its light curve was unlike anything seen before. Kepler was designed to find planets by spotting the regular, gentle dips in starlight caused by an orbiting world passing in front. Tabby's star did not dip gently. Its light would plummet by up to 22% in chaotic, asymmetrical plunges that lasted for days or weeks with no repeating schedule. This was not the signature of a neat, circular planet. It was as if something massive, jagged, and utterly irregular was repeatedly drifting in front of the star, blocking its light in a frantic, unpredictable dance. The immediate surprise for experts was the sheer scale of the dimming. To block that much light required an object or a collection of objects far larger than any planet. The hunt for a natural explanation began, each hypothesis stretching the limits of known astronomy. Could it be a vast, fragmented swarm of comets stirred up by a passing star? Perhaps it was the aftermath of a planetary collision, like the one at Fomalhaut but on a far grander scale, leaving a massive cloud of debris. Some astronomers even looked to the star itself, wondering if it was undergoing internal convulsions we had never before recorded. Yet each natural model struggled to fully account for the depth, irregularity, and long-term fading also seen in the star's overall brightness. It was this struggle that opened the door to a breathtaking, if speculative, possibility. In a galaxy of trillions of stars, could this be the signature of a Type II civilization on the Kardashev scale? The idea of a Dyson sphere, a hypothetical megastructure built by an advanced species to capture a star's entire energy output, moved from science fiction into a legitimate point of discussion. The irregular dips, the thinking went, could be caused by partially constructed swarms of orbiting collectors, their uneven shapes and orbits creating the bizarre light pattern. This was not a claim, but a stunned acknowledgement of how strange the data truly was. The subsequent years have seen careful follow-up observations, particularly with the Spitzer and Swift telescopes. A key clue emerged: the dimming was more pronounced in blue light than in infrared. This strongly suggests the material blocking the star is not solid, opaque megastructure, but fine, microscopic dust which scatters blue light more effectively. The current scientific consensus leans toward a natural, if extraordinary, explanation, likely involving immense clouds of dust from a disrupted moon or a family of exocomets. But the core mystery of its extreme and erratic behavior remains. Even a dust-based model requires a source for that dust and a mechanism to create such profound, aperiodic shadows. Tabby's star endures as a powerful symbol, a reminder that when we look deeply enough, the universe will present us with puzzles that challenge not just our models, but the very boundaries of our imagination, holding a space where wonder and rigorous science share the same data stream. Tabby's star taught us to expect the unexpected, but at the very largest scales, the universe was supposed to follow a pattern. After mapping the cosmic microwave background, astronomers developed a powerful model for how everything we see came to be. Those tiny primordial ripples, amplified by gravity over billions of years, should have drawn matter into a vast cosmic web, a filamentary structure of galaxy clusters and superclusters separated by great, but not entirely empty, bubbles. The distribution of galaxies across the heavens, they believed, should be like a sponge, matter and void in a predictable balance. Then, in the early 1980s, while conducting a large-scale survey of galaxy positions, astronomer Robert Kirshner and his colleagues pointed their telescopes toward the constellation of Bootes the herdsman. What they found there was not a filament or a bubble, but a staggering nothingness. They had discovered the Bootes void, a spherical region of space so profoundly empty it defied all reasonable expectation. The sheer scale was the first breathtaking surprise. This void is not a small pocket. It spans a region of space roughly 330 million light-years across. To grasp that immensity, if you placed our Milky Way galaxy at the center of this void, you would not have seen another galaxy until your telescope's gaze had traveled over 150 million light-years in any direction. In a universe supposedly filled with a web of matter, this was a cavern of incomprehensible size. The second shock was the census. A region of that volume, based on the average density of the cosmos, should contain at least 10,000 galaxies. Early surveys found only 60. Later, more sensitive observations have raised the count to a few thousand, but that is still a fraction of what the standard model predicts. It is not a perfect emptiness, but it is an extreme, yawning underdensity that challenges our understanding of how the large-scale structure of the universe forms. How could gravity, working on those initial seeds from the Big Bang, have cleared out such an immense volume of space? One compelling theory suggests that smaller voids, like the bubbles in our cosmic sponge, merged over time through a kind of gravitational feedback, where galaxies on the edges of a void were pulled toward denser regions, causing the void to expand and eventually swallow its neighbors. The Bootes void could be the ultimate result of that process, a supervoid formed by the consolidation of countless smaller empties, yet its existence remains a profound puzzle. It forces cosmologists to question whether the initial conditions of the universe were more varied than our baby picture suggests, or if there are forces and processes on the largest scales we have yet to comprehend. Gazing into the Bootes void is not looking at darkness, but at a question mark written in negative space, a silent reminder that even the grand architecture of the cosmos can hold gaps large enough to swallow our assumptions. The Bootes void is a staggering emptiness on the grandest scale, but on a single, frozen moon, the universe was quietly assembling the building blocks of something else entirely. Far beyond the asteroid belt, in the cold outer kingdom of Saturn, orbits a world that should not exist as we know it. Titan is larger than the planet Mercury, shrouded in a perpetual orange haze. For centuries, it was just a smudge of light, a featureless dot in even the most powerful telescopes. The assumption was that, like all moons, it would be a silent, airless ball of rock and ice. When the Voyager probes flew by in the early 1980s, they delivered the first stunning correction. Titan was not airless. It possessed a thick, substantial atmosphere, primarily of nitrogen, making it the only moon in our solar system with such a dense gaseous envelope. This alone was a monumental surprise, but it was only the opening act. The true shock required a visitor that could stay and look closer. That visitor was the Cassini Huygens mission. In 2005, the Huygens probe detached from the Cassini orbiter and began its historic descent through Titan's opaque clouds. What it revealed was a landscape of profound and eerie familiarity. Radar and imaging instruments pierced the haze to show river channels carving through hills, vast, dark plains, and shorelines bordering great, smooth expanses. But this was not a water world. On Titan, with surface temperatures dipping to -290 degrees Fahrenheit, water is frozen harder than granite. The liquid that sculpts this alien geology is methane and ethane, hydrocarbons that exist as gases on Earth but flow as rivers and pool into great lakes and seas on Titan's frigid surface. The Huygens probe even touched down on a damp, pebble-strewn plain that resembled a creek bed on Earth, sending back images of rounded stones shaped by flowing liquid methane. This discovery of active, liquid-based hydrology on another world was breathtaking, but the deeper surprise was in the air itself. Cassini's instruments sampled Titan's complex atmospheric chemistry, a rich soup of organic molecules. Sunlight breaks apart methane and nitrogen high in the atmosphere, triggering a cascade of reactions that create more complex hydrocarbons like ethylene and propane, and form nitriles, compounds rich in carbon and nitrogen. These molecules coalesce into a kind of soot that drifts down, coating the surface in a layer of organic sludge. Titan, in essence, is a factory. It is a world with all the machinery for prebiotic chemistry, the same kind of processes that on the early Earth, warmed by the sun, eventually led to the chemistry of life. Here, that same experiment is running in a deep freeze with methane standing in for water. It presents a haunting alternative pathway. Could the ingredients for life assemble in such a cold, alien solvent? We do not yet know, but Titan stands as a frozen, working analog to our own planet's distant past, a reminder that the universe's recipe book is far more varied and its experiments far more patient than we ever dreamed. Titan's frozen chemistry experiment revealed a world of unexpected activity, but it was another small, distant body that delivered the most visually stunning geological surprise of all. For decades after its discovery, Pluto was little more than a faint point of light, a frozen curiosity at the edge of everything. Even as telescopes improved, it remained a blurry pixel, a world assumed to be a simple, cratered ball of ice, a dead relic locked in a permanent deep freeze since the dawn of the solar system. Its geology, if you could even call it that, was thought to be a static record of ancient impacts, nothing more. Then, in July of 2015, NASA, a New Horizons spacecraft, screamed past after a 9-year journey, and its cameras began to stream back the first close-up images of this forgotten world. The initial photos were breathtaking, showing a complex, variegated surface with dark, cratered highlands and bright, smooth plains. But the image that stopped the world, the one that became an instant icon, was the one revealing a perfect, brilliant white heart. This was Tombaugh Regio, a vast, heart-shaped plain nearly 1,000 miles across, named for Pluto's discoverer. Its beauty was arresting, but for planetary scientists, its geology was shocking. The heart's left lobe, a region called Sputnik Planitia, was the real mystery. This was an immense basin filled with flowing glaciers of nitrogen ice, but it showed a surface almost completely devoid of impact craters. In the solar system, a craterless plain is a clock that has just been reset. Craters accumulate over billions of years, so a surface without them is telling you, in no uncertain terms, that something has happened very, very recently to erase them. On a small, cold world with no obvious internal heat source, this was supposed to be impossible. The absence of craters meant Sputnik Planitia was geologically alive. The nitrogen ice was not a static sheet, it was a fluid, churning cell. Scientists realized they were looking at a vast, convecting ice cap. Sunlight would gently warm the solid nitrogen, causing it to become buoyant and rise in great blobs, while colder material sank, constantly renewing the surface in a slow cosmic churn. This process required a source of internal heat, which forced a complete rethink of Pluto's interior. The leading theory points to a subsurface ocean of liquid water, kept from freezing by the decay of radioactive elements in Pluto's rocky core, and perhaps by the insulating effect of a thick, icy shell. This hidden warmth could provide the energy to drive geological activity, causing the icy crust to shift and renew itself. The heart of Pluto was not a sentimental symbol but a pulsating engine. It proclaimed that small, distant worlds were not inert tombs, but dynamic planets with their own hidden fires, capable of surprising us with their vitality long after we had written them off as dead. The heart of Pluto was a testament to hidden warmth, but in the silent reaches between galaxies, the universe was sending out pulses of pure, concentrated energy that seemed to defy all reason. In 2007, astronomer Duncan Lorimer and his student David Narkevic were sifting through archival data from the Parkes Radio Telescope in Australia, searching for new pulsars. Buried in the observations from 6 years earlier, they found something that should not have been there. It was a single 5-millisecond burst of radio waves, a spike of energy so intense it overwhelmed the instruments, appearing and vanishing in less time than it takes to blink. The signal, now known as the Lorimer burst, came not from within our galaxy, but from billions of light-years away. The initial reaction among experts was profound skepticism. A burst that powerful from such an immense distance would require a source of almost unimaginable energy, releasing in 1,000th of a second as much power as our Sun puts out in 80 years. Many assumed it was a local glitch, an artifact from Earth's atmosphere, or even a malfunctioning microwave oven at the observatory. It was too strange, too extreme to be real. Yet, as more sensitive telescopes began listening, they found more. Not just one anomaly, but dozens, then hundreds of these fast radio bursts. Each was a brilliant, solitary flash from a random point in the distant cosmos, a cosmic strobe light blinking once and never again. The mystery deepened exponentially when astronomers discovered that some of these bursts were not one-off events. They repeated. A source designated FRB 121102, discovered in 2016, began firing off bursts in an irregular, unpredictable pattern. This was the second, greater shock. A cataclysm powerful enough to vaporize a star could not happen twice from the same location. The repeating bursts meant the source was not destroyed. It was something that could produce these titanic explosions over and over again. The hunt for an explanation became one of the most urgent puzzles in astrophysics. The leading candidate points to the most magnetic objects we know, magnetars. A starquake on a supermagnetized neutron star, a crack in its crust unleashing a torrent of energy, could potentially create such a brilliant, brief flash. Observations in 2020 provided compelling evidence, linking a highly active magnetar within our own Milky Way to a burst that had all the hallmarks of a weaker, nearby fast radio burst. It was a crucial clue, suggesting magnetars could indeed be one engine for these phenomena. Yet, the sheer diversity of the bursts, with some repeating in complex patterns and others appearing from environments unlike any magnetar we know, suggests the universe may have multiple ways to create these brilliant radio screams. Some theories even involve exotic objects like collapsing neutron stars or interactions with black holes. The enduring surprise is that these millisecond flashes, these cosmic firecrackers from the edge of time, represent a fundamental language of the universe we are only beginning to hear, a language of such immense power that its very words remain a tantalizing, energetic secret. A world made of diamond sounds like the fantasy of a cosmic jeweler, but the universe has a way of turning our most extravagant dreams into scientific fact. Orbiting a sun-like star 41 light-years away is a planet named 55 Cancri E, a super-Earth with a secret written in its impossible density. Discovered in 2004, it is a world about twice the size of our own and nearly 9 times as massive. That extraordinary mass packed into such a relatively small volume gave astronomers their first major clue. This planet was incredibly dense, far denser than a rocky world like Earth. Initial models based on our own solar system suggested it should be a super-sized version of a terrestrial planet, a colossal ball of silicates and iron. But the numbers did not add up. Something exotic had to make up its bulk. The stunning revelation came from analyzing the chemical composition of its parent star, 55 Cancri A. Stars and the planets that form from them are born from the same cloud of material, so a star's composition is a recipe book for its planetary system. This star showed an unusually high ratio of carbon to oxygen. In our own solar system, the ratio favors oxygen, leading to planets built from oxygen-rich minerals like silicates, resulting in rocks and a great deal of water. In the 55 Cancri system, carbon was the dominant building block. This simple chemical shift changes everything about planetary formation. In such a carbon-rich environment, the protoplanetary disk would have been filled with carbon compounds like graphite and carbides. As a super-Earth formed close to its star in this disk, the immense pressures and temperatures in its interior would have acted like a cosmic forge, crushing that abundant carbon into its most stable, crystalline form. Researchers calculated that a significant portion of the planet's interior, perhaps up to a third of its mass, could be actual diamond. Imagine a mantle not of flowing rock, but of solid crystallized carbon, with a graphite crust above and perhaps a molten, carbon-rich core below. This is not a shiny, faceted gemstone floating in space, but a dark, searing hot, and geologically alien world. Its surface, if we could see it, might be a global landscape of graphite mountains slowly being recrystallized into diamond in the depths. The surprise of 55 Cancri E was a lesson in cosmic chemistry. We had always assumed that Earth, built from silicon and oxygen, was the standard template for rocky worlds. This diamond planet proved our solar system's recipe is just one of many. The universe can bake planets from entirely different ingredients, creating worlds of carbon where it rains tar, and the very ground is a precious stone, reminding us that the elements we value so highly here are merely common construction materials in the infinite workshop of the cosmos. The diamond world of 55 Cancri E-proved planets could form from alien recipes, but at the very edge of our sun's influence, a different kind of frontier was being mapped, not by light, but by the feel of an invisible wind. For decades, our model of the solar system's boundary was elegantly simple. The sun constantly emits a stream of charged particles, the solar wind, which carves out a protective bubble in the galaxy called the heliosphere. This bubble was thought to have a smooth, comet-like shape, with a clear boundary where the solar wind abruptly slowed as it met the pressure of the interstellar medium. This slowdown point was called the termination shock, and beyond it lay a calm, transitional region leading to the final wall, the heliopause, where the sun's influence truly ended and interstellar space began. It was a neat, theoretical diagram. Then our envoys, the Voyager probes, actually reached those distant coordinates, and the simplicity vanished. Voyager 1 crossed the termination shock in December of 2004 at a distance of about 94 astronomical units from the Sun. The data it sent back was the first great surprise. The shock was not a single, sharp barrier. It was a complex, rippling series of crossings, as if the probe was passing through a turbulent zone of overlapping waves. The solar wind was not slowing in a uniform way, it was surging and ebbing, revealing a dynamic, messy interface, but the deeper mysteries lay further out. In August of 2012, Voyager 1 made its historic exit, becoming the first human-made object to enter interstellar space. The telltale sign was a dramatic drop in solar wind particles and a corresponding spike in cosmic rays from the galaxy. Yet the magnetic field direction, which scientists expected to flip abruptly at the heliopause, did not change. This was baffling. It suggested the interstellar magnetic field was somehow aligned with the Sun's field, or that the boundary was far more porous and intertwined than anyone had predicted. Then Voyager 2 crossed the heliopause in November of 2018 from a different location. Its instruments told a similar yet distinct story. It also detected a surprisingly thick, smooth boundary layer that the solar wind had to filter through, and it confirmed the magnetic field puzzle. The data from both probes painted a stunning new picture. The heliosphere is not a sleek, solid bubble sailing through the void. Its outer layers are frothy and porous, more like a magnetic sponge or a collection of turbulent bubbles, where the solar and interstellar magnetic fields mix and connect. Even more surprising, the local interstellar medium was exerting a much stronger pressure on our solar bubble than models had predicted, squeezing it into a more rounded shape. This meant the galaxy's ambient wind, the collective breath of ancient supernova and stellar winds, was pushing back with unexpected force, shaping our entire cosmic neighborhood. The Voyagers, these silent travelers from the 1970s, had not just crossed a line, they had revealed a frontier of magnificent complexity, a magnetic labyrinth where the sun's breath finally dissolves into the greater ocean of the galaxy. The magnetic labyrinth at the edge of our solar system is a quiet frontier, but within the dense, ancient star clusters at the heart of the galaxy, a far more predatory relationship unfolds. There, astronomers have discovered a class of cosmic vampires, stars with a deadly embrace that has earned them a chilling name, the Black Widow pulsars. These are not ordinary pulsars. They are the rapidly spinning, super-dense remnants of massive stars, but they are almost always found locked in a tight, lethal orbit with a much smaller, ordinary companion star. The surprise came when researchers realized the true nature of this partnership. The pulsar's intense beams of radiation and a relentless torrent of charged particles are not just flashing into the void, they are bathing the nearby companion in a continuous, withering blast. This is not a gentle dance, it is a slow, cosmic evaporation. The pulsar's energy is so fierce it is literally boiling away the outer layers of its partner, stripping it down over millions of years. The image is stark, a stellar cannibal using its own brilliant energy to consume the very thing that holds it close. This extreme process solves a long-standing mystery about a different kind of pulsar, the millisecond pulsars. These are neutron stars that spin hundreds of times per second, far faster than any pulsar has a right to spin from its initial birth. The Black Widow provides the violent explanation. As the pulsar siphons material from its companion, that stolen gas doesn't just vanish. It carries immense angular momentum, and as it spirals onto the pulsar's surface, it acts like a cosmic whip, transferring its spin energy and accelerating the pulsar to those incredible speeds. The companion star, now diminished and ghostly, is left as a burnt-out cinder, a planetary-sized husk of its former self. The discovery of these systems was a revelation about the brutal evolutionary pathways forced upon stars in crowded environments. In the dense cores of globular clusters, where stars pass by each other like strangers in a packed crowd, such gravitational captures and subsequent feasting may be a common, if terrifying, way of life. It reveals a universe where even in death, a star can become a predator, spinning faster and shining brighter by slowly consuming the light of another. The predatory dance of Black Widow pulsars reveals a universe of stark, brutal relationships, but the most profound conflict in modern cosmology is not between stars, but between two sets of pristine measurements. We call it the Hubble tension, and it is a quiet, growing crisis that threatens to unravel our most trusted picture of cosmic evolution. The heart of the issue is a single, fundamental number, the Hubble constant. This figure describes how fast the universe is expanding at the present moment, the current rate at which galaxies are fleeing from one another. For decades, astronomers have strived to pin down this number with ever greater precision, confident that different methods would eventually converge on a single, universal truth. Instead, they have found themselves staring at two different answers, each backed by impeccable evidence, each refusing to agree with the other. The first method looks back to the universe's infancy, to the cosmic microwave background. By studying the minute temperature fluctuations in this ancient light with exquisite detail, missions like Planck can calculate the ingredients of the early cosmos, the amounts of dark matter, dark energy, and ordinary matter. Plugging these numbers into our standard model of cosmology, known as lambda CDM, allows scientists to predict how the expansion should have evolved over 13.8 billion years, arriving at a present-day expansion rate. This early universe measurement is incredibly precise. The second method works locally, measuring distances and speeds of objects in our modern cosmic neighborhood. Astronomers use celestial mile markers called Cepheid variable stars, whose predictable pulsations reveal their true brightness, and the brilliant explosions of Type 1a supernova, which act as standard candles. By carefully calibrating the distances to these beacons in nearby galaxies, they can measure how fast those galaxies are moving away from us, giving a direct present-day value for the Hubble constant. Both methods are pillars of modern science refined over generations. The stunning and deeply troubling result is that they do not match. The early universe measurement from Planck suggests a slower, more stately expansion, around 67 kilometers per second per megaparsec. The local measurements from supernova and Cepheids point to a faster, more hurried cosmos, around 73 kilometers per second per megaparsec. The difference seems small, only a few percent, but the precision of each measurement is now so high that the gap is statistically significant. It is not an error, it is a stubborn, persistent discrepancy. This has sent a ripple of profound concern through the cosmology community. For years, researchers checked and rechecked for hidden systematic errors, a miscalibrated instrument, a misunderstood property of dust, or a bias in the stellar data. Yet as observations improve, the tension does not ease, it tightens. The unsettling implication is that our cherished standard model of cosmology, which has beautifully explained so much about the universe's structure and history, may be incomplete. The discrepancy hints at new physics, an ingredient or a rule we have not yet accounted for. Perhaps dark energy is not a constant, but an evolving force that has changed strength over cosmic time. Maybe dark matter has properties we have not yet detected, or our understanding of gravity itself requires a subtle modification on the largest scales. The Hubble tension is more than a technical disagreement. It is a cosmic whisper that the story we have written for the universe, for all its success, might be missing a crucial chapter, a revelation waiting in the gap between two impeccable numbers. Our solar system's current arrangement feels like a permanent clockwork, with each planet tracing its stately, predictable orbit. For generations, this was assumed to be its original state, a system that formed neat and orderly and simply stayed that way. The giant planets Jupiter, Saturn, Uranus, and Neptune were thought to have coalesced right where we see them today, massive anchors holding the rest of the architecture in place. This picture of a static, unchanging family portrait was comfortable and intuitive. Then, computer models began to probe the dynamics of the early solar system, and that comfortable picture shattered. The simulations revealed something astonishing. The giants did not stay put. In the chaotic first few hundred million years after their formation, they went on a grand tour. This idea, most famously captured in what scientists call the Nice model, proposes a dramatic reshuffling. Initially, the four giant planets may have orbited much closer together in more compact circular paths. Surrounding them was a vast disk of leftover icy planetesimals, the building blocks that never became planets. As these small objects interacted gravitationally with the giants, a slow-motion dance began. The planets, particularly Jupiter and Saturn, began to exchange energy with this sea of icy debris. Jupiter, the most massive, likely drifted slightly inward. Saturn, Uranus, and Neptune, in a complex gravitational interplay, were pushed outward. This was not a gentle drift. It was a violent migration that sent gravitational shockwaves through the entire young system. The consequences of this planetary parade were catastrophic for everything else. As the giants moved, their immense gravity acted like a cosmic flail, hurling thousands of those icy planetesimals in all directions. Some were sent careening into the inner solar system, becoming the comets we see today. Others were flung outward to form the distant Oort cloud. A vast population of asteroids was also violently scattered, their stable orbits disrupted. This period of chaos provides a compelling explanation for one of the most dramatic chapters in our planetary history, the Late Heavy Bombardment. Geological evidence on the Moon, Mercury, and Mars shows that around 4 billion years ago, after the planets had largely formed, the inner solar system was suddenly and violently pummeled by a rain of impactors. For decades, the source of this cataclysm was a mystery. The migrating giant model offers a stunning answer. It was the gravitational fallout from their great migration. The timing fits perfectly. As Jupiter and Saturn shifted, they destabilized the asteroid belt and the primordial disk, directing a fusillade of material toward the inner planets. This reshuffling did not just move planets, it sculpted the final layout of our entire system, determining which worlds would be rocky and close to the Sun, and which would be gaseous and distant. It may even have influenced Earth's own history, as those bombardments could have delivered water and organic compounds. The realization that our solar system's architecture is not a birthright, but the aftermath of a turbulent adolescence, forever changed our view of planetary systems everywhere, suggesting that such dramatic rearrangements might be a common and violent part of growing up for stars and their families. The Great Migration of the Giants was a violent reshuffling of our own cosmic neighborhood, but to witness the true dawn of cosmic structure, we must look back to a time when the universe itself was in its infancy. For decades, cosmologists had crafted a detailed and elegant timeline for the universe's first chapters. After the Big Bang came the cosmic dark ages, a period of cooling, expanding fog. Then, gravity began its patient work on the tiny seeds seen in the cosmic microwave background, slowly pulling together the first clumps of dark matter and gas. According to the models, it should have taken hundreds of millions, even a billion, years for these primordial clouds to collapse, ignite their first stars, and assemble into anything we would recognize as a proper galaxy. The first galaxies, the theory went, would be small, fragile, and chaotic, the cosmic equivalent of toddlers, messy, unformed, and fundamentally simple. This was the established story, the expected progression from darkness to dawn. Then, the James Webb Space Telescope opened its golden eye, designed to see the universe's first light in unprecedented infrared detail. It was a time machine pointed at the era of cosmic sunrise. When its first deep field images were analyzed, the scientific community was met not with confirmation, but with a collective gasp. Scattered across those deepest fields were not just a handful of faint, infant smudges. There were dozens of galaxies, and they were not toddlers. They appeared massive, structured, and shockingly mature, existing at a time when the universe was only 300 or 400 million years old, a mere 3% of its current age. This was like finding a fully grown, thriving metropolis in the archaeological record of a civilization that was supposed to be just learning to farm. The sheer number and apparent size of these galaxies presented an immediate and profound puzzle. How could so much stellar mass assemble so quickly? How could gravity work its magic at a pace that seems to defy our best simulations? The surprise from Webb is not a single anomalous object, but a population, a whole crowd of cosmic early birds that should not exist in such abundance. This discovery is currently forcing a dramatic rethink of the universe's first billion years. Theorists are now exploring radical ideas to explain this accelerated growth. Perhaps the first stars were unimaginably massive and short-lived, seeding the cosmos with heavy elements at a breakneck pace. Maybe early black holes played a far more active role in galaxy formation than we thought, their voracious feeding and energetic outflows jump-starting star formation. Or it could be that our understanding of dark matter's behavior in those first moments needs a fundamental revision. Each of these galaxies in Webb's deep field is a question mark written in ancient starlight, challenging the very timeline of cosmic evolution. They are not just rewriting a chapter, they are suggesting the universe's childhood was far more dynamic, productive, and astonishingly brief than our most careful stories ever allowed. While Webb's deep fields reveal galaxies born impossibly early, our own sun conducts a more intimate daily drama of creation and destruction in its own atmosphere. High above its blazing surface, in the region called the corona, temperatures soar to millions of degrees, a mystery in itself. Yet within this inferno, something utterly counterintuitive occurs, a storm of fiery rain. This is coronal rain, and its discovery revealed a sun far more dynamic and hydrologic than anyone had imagined. For decades, the corona was viewed as a tenuous, superheated halo, a static crown of plasma where physics operated at extremes. The idea of anything resembling weather, let alone precipitation, in that multimillion-degree furnace seemed absurd. Rain requires a cycle of condensation and fall, a process belonging to the relatively cool, dense atmospheres of planets, not to the thin, scorching gases of a star. The first observations of this phenomenon, however, came from spacecraft like the Solar Dynamics Observatory, which watches the sun in multiple wavelengths of light. Their high-resolution movies captured something breathtaking. Along the immense, arching magnetic loops that tether the sun's surface, brilliant droplets of plasma would form, not at the solar surface, but hundreds of thousands of kilometers up in the corona itself. These droplets, each larger than our planet, would then plummet along the curved magnetic pathways, accelerating downward in a fiery downpour back to the solar surface. The visual similarity to water droplets sliding down a curved window pane was uncanny, yet the physics were alien. Here was rain falling from a sky hotter than the core of a nuclear explosion. The surprise for solar physicists was not just the beauty of the spectacle, but what it implied about the corona's hidden machinery. Coronal rain is the cooling phase of a violent heating cycle. The sun's tangled magnetic fields are constantly injecting energy into the corona, superheating the plasma. But in some regions, that plasma becomes so dense it can no longer be held aloft by the magnetic pressure. It rapidly cools, condensing from a diffuse, multimillion-degree gas into these colossal, relatively cooler clumps still searing at around 10,000 degrees. Gravity then takes over, pulling these condensed globs of plasma down the magnetic lanes in a dramatic, looping freefall. This process revealed that the corona is not a uniformly hot, stable blanket. It is a seething, dynamic place of localized, intense heating and sudden, catastrophic cooling, a stellar weather system where magnetic storms brew and dissipate in a continuous, fiery deluge. Watching coronal rain is like seeing the sun's own circulatory system in action, a vivid demonstration that even the most extreme environments in our universe are governed by cycles of rise and fall, of energy spent and reclaimed in a perpetual, majestic storm. The sun's fiery rain is a spectacle of magnetic weather, but in the quiet gravitational lanes of Earth's own orbit, a different kind of celestial companion was waiting to be found. For over 2 centuries, astronomers have understood a beautiful quirk of orbital mechanics, the Lagrange points. These are 5 positions in space where the gravitational pull of a large body, like the Sun, and a smaller one, like Earth, perfectly balance with the centrifugal force of a smaller object's orbit. Think of them as cosmic eddies, places where the flow of gravity creates a pocket of stability. 2 of these points, known as L4 and L5, lie along Earth's orbital path, one 60 degrees ahead of our planet and one 60 degrees behind, forming the points of 2 vast equilateral triangles with the Sun. Theory long predicted that small objects like asteroids could become trapped in these gravitational sweet spots, traveling around the Sun locked in step with Earth, never falling behind and never racing ahead. These hypothetical objects were called Trojan asteroids, named for the pattern first seen with Jupiter, which has thousands of such companions. Yet for our own planet, the search came up empty for generations. The prevailing assumption was that Earth's Lagrange points were too dynamically unstable over the long term, that any small object would be easily perturbed by the gravity of Venus or Mars and kicked out of its delicate balance. Earth, it seemed, traveled alone. That assumption held until 2010, when astronomers analyzing data from NASA's Wide-Field Infrared Survey Explorer spacecraft spotted a faint object in Earth's leading Lagrange point L4. Designated 2010 TK7, it was our first confirmed Trojan, a rocky companion roughly 300 meters across, dancing ahead of us in the void. The discovery was a quiet but profound surprise, proving that these stable pockets could indeed harbor material over astronomical timescales, even for a planet with close planetary neighbors. But the bigger shock came just a few years later. In 2020, a second, far more significant Trojan was discovered, not at L4, but at Earth's trailing Lagrange point L5. This asteroid, named 2020 XL5, is estimated to be over 1 kilometer in diameter, making it the largest known Trojan companion of our planet. Its size and stability suggest it is not a recent temporary capture, but a primordial resident, likely orbiting in that gravitational haven for billions of years, a silent witness to Earth's entire history. Finding these hidden travelers reshapes our understanding of our immediate cosmic environment. They are not just curiosities, they are time capsules. Trapped in stable orbits with minimal thermal processing from the Sun, these asteroids could preserve some of the most pristine material from the inner solar system's earliest days, a record potentially cleaner than anything on the Moon or even most near-Earth asteroids. This makes them irresistible targets for future robotic and perhaps even human exploration. A mission to a Trojan would be a journey to a gravitational island, a place where a spacecraft could park with minimal fuel, studying an ancient world that has shared our annual journey around the Sun since before life began on Earth. Their existence is a gentle reminder that even in the orbit we think we know so well, there are still hidden neighbors waiting in the gravitational shadows, holding secrets from the dawn of our own world. But even our planet's hidden Trojan companions move within the familiar, predictable pull of our Sun's gravity. At the very largest scales, where the universe should be expanding in a uniform, stately drift, astronomers found a current moving against the tide. This mystery is called the dark flow, and its detection was a shock that seemed to pull at the edges of reality itself. The discovery came from studying the cosmic microwave background, that ancient afterglow of the Big Bang. This light is not perfectly uniform. It carries a subtle, predictable pattern of hot and cold spots, but it also holds a more subtle fingerprint, a Doppler shift caused by the motion of galaxy clusters as they travel through space. By carefully mapping the motions of over 1,000 massive clusters, researchers led by Alexander Kashlinsky made an announcement in 2008 that sent ripples of disbelief through cosmology. They reported that these enormous conglomerations of galaxies, each containing thousands of individual star systems, were not drifting randomly. Instead, they appeared to be streaming together in a coherent, bulk motion toward a single patch of sky, at a staggering velocity of nearly 2 million miles per hour. This was not just surprising, it was theoretically forbidden. On the grandest scales, the universe's expansion should be the dominant motion, with any additional movements caused by the gravitational pull of nearby, massive structures like the Great Attractor. But the scale of this dark flow was the problem. It involved clusters spread across billions of light years, a volume so immense that no known concentration of matter within our observable universe could possibly generate such a vast, coordinated pull. The gravitational influence of even the largest superclusters should have faded into the uniform background at such distances. It was as if every ship on an ocean, no matter how far apart, was being tugged by a current whose source lay beyond the horizon. This is where the surprise deepened into profound speculation. If the flow's source was not within our observable universe, where could it be? One breathtaking, if highly controversial, hypothesis emerged. Perhaps the dark flow was evidence of a gravitational tug from something entirely outside our cosmic bubble. In the multiverse concept, our universe might be one of many, like a bubble in a vast cosmic foam. If another universe bubble existed extremely close to our own in a higher dimensional space, its immense mass could, in theory, exert a gravitational influence across the boundary, gently pulling on the matter within our entire observable cosmos like a distant magnet. This idea was as stunning as it was untestable with current technology, suggesting we might be feeling the breath of another reality entirely. The result, however, has been fiercely contested from the start. Other teams analyzing different data have failed to detect the flow, or have argued that the statistical methods used could be biased by foreground emissions from our own galaxy or incomplete cluster catalogs. The debate remains unresolved, a tense standoff between an extraordinary claim and the extraordinary evidence required to support it. Whether the dark flow is a real cosmic current or a statistical mirage, its very proposal opened a door in the scientific imagination, forcing experts to consider that the ultimate source of a mystery might not lie in the stars we see, but in the unseen architecture of everything that lies beyond. The dark flow suggested a universe pulled by unseen horizons, but a single, familiar star in our own night sky staged a drama that felt both intimate and apocalyptic. In late 2019, the constellation Orion, that iconic winter hunter, began to look strangely unbalanced. Its brilliant shoulder, the red supergiant star Betelgeuse, was fading. This was not a subtle shift noticed only by telescopes. It was a change visible to the naked eye. Over weeks and months, the star's brightness plummeted by nearly 2/3, dimming to its faintest level in over a century of recorded observations. For astronomers and stargazers alike, the sight was deeply unsettling. Betelgeuse is a massive, aging star, a ticking cosmic clock known to be in the final stages of its life. It is the type of star destined to end its existence in a supernova, a cataclysm so brilliant it could outshine the full moon and be visible in broad daylight. The Great Dimming, as it came to be called, sparked a wave of electrified speculation. Was this the prelude? Were we witnessing the final, frantic convulsions of a star about to die in a spectacular flash that would be seen across the galaxy? The possibility that a nearby star, a mere 640 light-years away, could go supernova in our lifetime was a breathtaking, once-in-a-civilization event. For a few months, the world watched the sky with a mixture of scientific fervor and primal awe, waiting for a light that never came. Instead of a final explosion, Betelgeuse gradually began to recover its brightness through 2020. The question remained, what had caused such a dramatic dimming, if not an imminent collapse? The answer came from a symphony of observations across different wavelengths of light. While the star had dimmed dramatically in visible light, observations in infrared showed a much smaller change. This was the crucial clue. Interstellar dust, which scatters and blocks blue and visible light, is largely transparent to longer infrared wavelengths. The pattern pointed not to something happening within the star's core, but to something passing in front of it. The leading explanation is a stunning act of cosmic self-obscuration. In the final phases of a red supergiant's life, it becomes unstable, pulsating like a colossal, irregular heart. These pulsations can launch enormous plumes of gas from the star's surface out into space. As this ejected material cools in the frigid vacuum, it can condense into vast clouds of silicate dust, essentially soot on a stellar scale. Astronomers now believe that just such an event occurred on Betelgeuse. The star likely expelled a titanic cloud of hot gas from a region on its southern hemisphere. As that cloud cooled and drifted outward, it condensed into solid dust grains, forming a temporary veil that partially blocked our view of the star's surface. We were not seeing the star die, we were seeing it shed a part of itself. This explanation transformed the event from a potential death knell into a rare and valuable lesson. The Great Dimming offered a front-row seat to the kind of violent mass loss that precedes a supernova. It showed us that these giant stars do not go quietly, but in fits and starts, coughing out their own material in preparation for the final act. Betelgeuse's recovery was a reassurance that the grand finale is not yet here, but its brief dimming was a profound reminder, a dress rehearsal written in shadow and dust, showing us how a star begins its long goodbye. Betelgeuse's great dimming was a lesson in stellar farewells, but sometimes the universe sends travelers that require no farewell at all, because they were never ours to begin with. For all of human history, every comet and asteroid we have ever tracked was a member of our own solar system's family, born from the same primordial cloud as our Sun. The idea of a visitor from another star was a staple of science fiction, a theoretical possibility that seemed forever out of reach, lost in the unimaginable vastness between stars. Then, on October 19, 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving at a speed and on a trajectory that was immediately, shockingly wrong. This object, soon named Oumuamua, a Hawaiian term meaning scout from the distant past, was not orbiting our Sun. Its hyperbolic path and incredible velocity meant it was just passing through, a cosmic tourist on a one-way trip from interstellar space. The confirmation was a historic first, but the real surprises were in the details. As telescopes around the world raced to study it, they found a shape unlike anything in our solar system. Based on how its brightness varied dramatically as it tumbled, astronomers deduced Oumuamua was highly elongated, perhaps 10 times as long as it was wide, resembling a cigar or a pancake tumbling through the void. This was bizarre, as most solar system asteroids are more lumpy or spherical. Then came the second, deeper puzzle. As Oumuamua sped away from the Sun, its trajectory could not be explained by gravity alone. It was accelerating ever so slightly, as if being given an extra, invisible push. For comets, such non-gravitational acceleration is common, caused by jets of gas erupting from heated ice on their surface. But Oumuamua showed no coma, no tail, no visible outgassing whatsoever. It was as dark and inert as a stone. This combination of traits, the interstellar origin, the strange shape, and the mysterious acceleration, ignited a firestorm of debate. Was it a bizarre, primordial asteroid made of exotic materials? Was it a comet after all, with hidden ices venting in a way we could not detect? The lack of a visible coma led some, like astronomer Avi Loeb, to propose even more extraordinary possibilities, suggesting its acceleration could be explained by the pressure of sunlight on a very thin, lightweight object, perhaps a solar sail of natural or even artificial origin. While most scientists favor a natural explanation, such as outgassing from a carbon-rich crust or the release of trapped hydrogen gas, the core truth is that Oumuamua departed our neighborhood before we could ever get a clear look, leaving behind a trail of unanswered questions and the profound realization that we had finally touched, however briefly, a piece of another star system. Just 2 years later, the universe sent a second clarifying postcard. In August 2019, amateur astronomer Gennady Borisov in Crimea spotted a new fuzzy object. Designated 2I/Borisov, it was unmistakably a comet with a brilliant coma and a clear tail streaming behind it. Spectroscopic analysis confirmed it was truly interstellar, and its composition was fascinatingly familiar, laden with carbon monoxide and water ice. Unlike the enigmatic Oumuamua, Borisov was a welcome open book, behaving exactly like a comet from our own Oort cloud, just one born around a different sun. This pair of visitors has opened an entirely new field of astronomy. Oumuamua showed us that interstellar objects can be utterly strange, challenging our categories. Borisov showed us they can also be wonderfully familiar, suggesting the ingredients for comets, and perhaps the processes that form planetary systems are universal. Together, they prove our solar system is not an island, but part of a vast, interconnected archipelago, where material occasionally drifts from one stellar shore to another, carrying with it the untold stories of distant suns. The Moon's surface is a museum of impacts, a stark record written in craters and grey dust. Yet across this monochrome landscape, astronomers have long noted delicate, brilliant graffiti, bright swirling patterns that curl across the plains like cosmic brushstrokes. The most famous is Oumuamua, a tadpole-shaped smear of dazzling white, nearly 40 miles long, sitting defiantly on the dark volcanic plains of Oceanus Procellarum. For centuries, these features were simply curiosities, assumed to be strange variations in the lunar soil, perhaps the ejecta blankets of long-vanished impacts. The first surprise came when scientists tried to map them against the Moon's topography. The swirls bore no relation to the hills and valleys beneath them. They were not raised or depressed, they were simply painted onto the surface, a pattern with no physical depth, like a tattoo on the Moon's skin. This ethereal quality made them a perfect lunar mystery, a visual phenomenon with no obvious cause. The key to unlocking part of the secret arrived with the Apollo missions and later orbital mappers. Instruments revealed that each of these bright swirls sits directly atop a localized, powerful magnetic anomaly. Unlike Earth, the Moon has no global magnetic field, but these swirls are anchored to pockets of magnetized crust, creating miniature magnetic bubbles that rise from the ground. This connection provided the stunning explanation for their persistence. The lunar surface is constantly bombarded by the solar wind, a stream of charged particles from the sun that slowly darkens and reddens the soil over time, a process called space weathering. It is why older lunar regions appear darker, but at the swirls, those miniature magnetic fields act like invisible umbrellas. They deflect the solar wind, shielding the soil beneath from that relentless darkening rain. The bright swirls are not deposits of strange material. They are simply the Moon's original, unweathered face, preserved for perhaps billions of years under these magnetic parasols. This solved the mystery of their brightness, but it immediately created a deeper, more profound puzzle. Where did these isolated, powerful magnetic fields come from? The Moon's core is not active enough to generate them now. One compelling theory points to the violence of the Moon's past. When large asteroids struck the lunar surface, the immense heat and pressure of the impact could have vaporized iron-rich material. If this vapor cloud expanded through a pre-existing, weak magnetic field from the Sun or the early Moon, it could have magnetized the iron as it settled back to the ground, freezing a magnetic signature into the crust at the moment of impact. Another idea suggests the fields are remnants from the Moon's own ancient global magnetic field, which faded eons ago, leaving only these stubborn, fossilized traces. Yet neither theory fully explains the precise, swirling shapes or the incredible strength of some anomalies. They remain enigmatic landmarks telling a story in two parts: the beautiful, preserved surface we can see, and the hidden, fossilized force field we cannot, a reminder that even our closest celestial neighbor keeps its most elegant secrets guarded by invisible shields. From the Moon's magnetic graffiti to the whispers of other star systems, this journey through 35 cosmic surprises reveals a universe that thrives on the unexpected. Each moment of expert astonishment, from the hellish surface of Venus to the accelerating expansion of space itself, was not a failure of science but its ultimate triumph. These were the cracks in our understanding through which a brighter, stranger light poured in, forcing us to rewrite textbooks and rethink our place in the cosmos. They are humbling reminders that the universe's imagination far exceeds our own, operating on scales and with creativity we are only beginning to perceive. The pattern is clear. Every shocking revelation, once absorbed, becomes the foundation for the next question, the new normal from which future surprises will spring. Today's impossible mystery is tomorrow's chapter in a textbook, a stepping stone for the next generation of explorers. And that next generation is already at the door, armed with tools that will undoubtedly deliver fresh shocks. The James Webb Space Telescope is peering into the cosmic dawn, finding galaxies too old to exist, Upcoming missions will probe the icy oceans of Europa and Titan, searching for signatures of alien biology. Giant ground-based telescopes will dissect the atmospheres of distant worlds, while gravitational wave observatories listen for the ripples from collisions we cannot see. Each new eye we open on the cosmos promises not just answers but better, more profound questions. The story is not ending, it is accelerating, so keep looking up and keep wondering. The greatest surprises are still out there, waiting in the dark for the moment they will once again leave us all, even the experts, in a state of awe. If you want to be there for those next revelations, make sure to subscribe and join us as we continue to explore the deepest mysteries of space, one shocking discovery at a time.